Welcome everybody to this Felix Klein lecture series in 2020. So this year it's done by Markus Reineke and it's about Quiver moduli and applications. So maybe I should say a little bit about this Felix Klein lectures. So they were introduced probably something like 10 years ago and are part now of our big graduate school program. So they happen every year, and there's every year we choose a different speaker from some different fields. And the idea is that it should really bring people together from pure mathematics. So one should start talking about these things, and it should the talk should start on a general level so that everybody can follow, and then also show somehow new developments in the last few years, hopefully. And everybody is, of course, welcome to interact and ask questions. So everybody, of course, knows Felix Klein, and maybe he is one of the few mathematicians who is really well known for his broad knowledge. Maybe it wouldn't be possible nowadays anymore, but somehow I think he very nicely reflects the idea of this lecture series. So I think I just give the words now to Peter and to Markus, and I hope you will enjoy the lectures.
Thank you. Markus, can you speak? Can you say a little bit? We don't hear you.
Yeah, I can speak a little bit. Is it
now we hear you. Yeah, this is perfect.
Wonderful.
So you're ready to go. We can start. Recording has started, so you're good to go.
Yeah, thank you very much. Thanks for the invitation to these Felix Klein lectures. There will be 5 of them, and this is episode 1 today. And thanks for everyone for participating. And so the title is Quiver moduli spaces and applications. And let me try to somehow summarize the idea of this lecture series in 2 sentences. So what are these Quiver moduli spaces? And so very informally, Quiver moduli spaces are spaces, geometric objects. More precisely, we will work in algebraic geometry, so there will be algebraic varieties, even complex algebraic varieties. And they encode the continuous parameters of certain classification problems. Encoding the continuous classification parameters of hard linear algebra problems. So that's what Quiver moduli spaces do for us in 1 sentence. And we will look at these hard linear algebra problems in the first motivational part of this talk. And I will present some classical hard and not so hard linear algebra problems. And then we will see step by step in the talk today and in the talk tomorrow how to define geometric objects which encode the continuous classification parameters, whatever this means precisely. So that's the one thing. This is what are these Quiver moduli spaces? And another question is, of course, how they feel. And I will try to present some examples, maybe pose some problems for you, and which we can discuss during the talks. And the other thing which I want to tell you about is applications. So quite surprisingly, at least for me, in the last 20 years or so, these Quiver moduli spaces appeared in several different areas, not as Quiver moduli spaces, but they calculated certain things which are hard to calculate. This is the second part of this aim. Sometimes they calculate, whatever this means. So how do geometric objects calculate something for us? This we will see. Sometimes they calculate hard things. For example, they calculate for us quantum dilogarithm identities. Sometimes they calculate for us certain Gromov-Witten invariants. Sometimes they calculate for us certain very difficult Euler product factorizations. So these are some of the most surprising applications because a priori it has nothing to do with linear algebra problems. And well, for physicists, they compute so-called BPS state counts and so on and so on. So quite surprisingly, these classification spaces for linear algebra problems calculate things which have nothing to do with linear algebra or with quivers. Quivers. Okay, so I will not assume any knowledge on quiver representations, and I will try to give all the necessary definitions about quiver representations, how they behave and how they feel. And then I will also explain to you when we concentrate on the moduli spaces, which parts of the theory of quiver representations we will not deal with, because we're interested in more geometric things, but we will come to this. Okay, so but this is somehow a two-sentence summary of what I will try to explain. And I will also try to keep some things a bit informal and not formulate theorems precisely, just to give you kind of a feeling for the subject. Because if you're new to the subject, then all this feels very strange, and somehow a more suggestive formulation or some bit more informal theorem might help to somehow guide you in the right direction without the theorem being too precise, which would require lots of additional notation or whatever. Okay, so as a motivational introduction, let me present to you some classification problems of linear algebra. Some classification problems in linear algebra. I think this is quite a good starting point because it's completely non-technical, except that we have to know what are vector spaces, linear maps, what are matrices, and what are row and column operations on matrices. And we all learn about this in the first year of studies, and I thought that's a good starting point. So, and well, if you already know about quiver representations, then this first part might be boring for you. You can immediately spot the quiver which I'm talking about, but nevertheless, let's somehow go back to this very beginning of quiver representation theory where you just post linear algebra problems. So let me call these problems A1 to A3, B1 to B3, C1 to C3, because after posing these problems, I want to draw a certain table and somehow putting them in place. First problem is, oh, okay. I work all the time over the base field of complex numbers, which is mostly synonymous for algebraically closed field of characteristic 0. Of course, you might always ask the question about generalization to positive characteristic or to non-algebraically closed field. And well, the general answer would be these linear algebra problems, which we would like to tackle, are so hard that we are happy if we can do something over the complex numbers. And if we can do something, then maybe later we can ask about positive characteristic and different fields, but let me just stick to the complex numbers all the time. So A1, classify finite dimensional complex vector spaces up to isomorphism. And we all know from linear algebra the solution: vector spaces up to isomorphism are classified by their dimension. Classified by the dimension of the space, which is one discrete invariant, a non-negative integer. Wonderful. Okay, so that's one of the first theorems of linear algebra, that we can classify the vector spaces. A1, A2, let's classify endomorphisms of a vector space. Or if you prefer the matrix language, let's classify square matrices up to congruence. Classify square matrices A, an n by n matrix over the complex numbers, up to conjugation. And conjugation means two matrices are called similar if and only if we can obtain B as S times A times S inverse, where S is an invertible matrix. So an element of the general linear group. Or in coordinate-free language, you could say we want to classify endomorphisms of vector spaces, finite dimensional vector spaces, up to base change. That's also something we learn in linear algebra, and the solution over the complex numbers, that's where we need them for the first time, is the Jordan canonical form. And in the Jordan canonical form, you have several invariants of such a matrix up to conjugation. One invariant is of discrete nature, the sizes of the Jordan blocks which are involved, and the other is of continuous nature, namely the eigenvalues of the matrix. So this is classified by the Jordan canonical form. And we have discrete parameters. These are the sizes of Jordan blocks. And we have continuous parameters. These are the eigenvalues of the matrix. So we have continuous parameters. It's clear that this will be important because I already told you that we want to define geometric objects encoding the continuous classification parameters. So it's clear that this will play a certain role. What is interesting here to know is that how many continuous parameters do we have? Well, counted with multiplicities, the number of eigenvalues is just the size of the matrix, so n. Yeah? N continuous parameters for classifying n by n matrices. All right, so that was A2. And A3 is now the problem. Let's classify pairs of square matrices up to simultaneous conjugacy. And the important thing is simultaneous. So we want to have one invertible matrix S and have a certain normal form for both matrices at the same time. This I will first formulate. So problem A3. This is the problem of simultaneous conjugacy. So we take a pair A prime. This is a pair of square matrices. And we say that two such pairs, A and A prime, are equivalent or simultaneously conjugate if and only if we can write B as S times A times S inverse and B prime as S times A prime times S inverse, again for S some invertible matrix. Yeah, so we're looking for one matrix bringing both A and A prime to some normal form. And this is an unsolved problem of linear algebra. This is unsolved. And one of the main problems why this is unsolved is that it depends on many, many continuous parameters. The number of continuous parameters which is involved grows quadratically with n. The more precise statement will follow later. That's one of the typical problems here. And if you try to do this practically, well, the first very obvious idea is, well, okay, I can just consider A and bring A to Jordan canonical form, and then ask for those conjugations S, which do not destroy the Jordan canonical form for the first matrix, but maybe bring the second matrix to some better form. And if you start doing this, it will become a complete mess. You can do it for pairs of 2 by 2 matrices, maybe for pairs of 3 by 3 matrices, but after that, it's a complete mess, and you don't see the pattern, and it's a, well, that's why this is an unsolved linear algebra problem. Okay, let me write down a second series of problems. B1 is, let's classify one linear map up to base change. Or in matrix language, let's take a rectangular matrix and perform row and column operations on it. Classify rectangular matrices A. This is now an M by N matrix. Up to the following notion of equivalence. A is equivalent to B if and only if B arises from A by S times A times T inverse, where S is an invertible M by N matrix and T is an invertible N by N matrix. So in more invariant terms, A defines a linear map between two vector spaces, and we want to classify linear maps up to base change in the source and the target space. Yeah? And these two base change matrices are S and T. And that's also something we learn in linear algebra. When we are talking about the Gauss elimination algorithm, if we have an arbitrary matrix and we are allowed to perform both row and column operations, we can simplify any matrix to the standard form. So we have a normal form, which looks like you have a unit matrix of a certain size here, and the rest is 0. So, and this classification is, again, discrete. It depends on 3 discrete parameters, namely the size of the matrix, M and N, and the number of ones in this normal form, which is nothing else than the rank of the matrix. Yeah. So the size of this block of ones is just the rank of the matrix. So it's a discrete classification, 3 discrete parameters. Okay, that's also something we know from linear algebra. What we don't know usually from linear algebra is do the same for pairs of matrices. And this goes under the name of pencils of linear maps. So let's say that A and A prime again are both rectangular matrices of the same size. And we want to classify them again up to row and column operations. But again, we want to perform these row and column operations simultaneously on both matrices. Well, this looks like a bad idea, yeah, like with the simultaneous conjugation, which is an unsolved problem. But in fact, this can be solved. And it's not much harder than the Jordan canonical form for one endomorphism. That's the surprising thing, but it's indeed a theorem. So again, let me call B prime equivalent to A prime if we can write B as S times A times T inverse, and simultaneously B prime as S times A prime times T inverse, again for S and T invertible matrices. So this problem was solved by Reineke in 1890 under the name of pencils of linear maps. Classified by Reineke. And the solution involves discrete parameters, in fact, many of them, which I will not explain, and continuous parameters, which are more or less of the same type as for one endomorphism. So just something like relative versions of eigenvalues. Discrete parameters plus continuous parameters if you want to see these continuous parameters in a simple example, so let me please ignore the discrete parameters. They are of course very interesting, but to write them down in detail would be a bit technical. If you want to see how some eigenvalues enter here, you can look at the following pairs. Take a pair consisting of a unit, n by n unit matrix, and then an n by n Jordan block involving some eigenvalue lambda. So this would be one of the typical building blocks of this theorem. In fact, here, the lambda can be an element of CP1. So infinity is something allowed because you can rescale the infinity and put a Jordan canonical form here. But this is maybe not so important for the second. But somehow the number of continuous parameters is still under control because it's as complicated as the Jordan canonical form. And now you might guess what problem B3 is. That's triples of linear maps, or triples of matrices. Same for triples of rectangular matrices. And again, then you encounter an unsolved problem. All right. Let me check for the time and maybe do a third series of problems, but only very briefly. Let's consider tuples of subspaces in a vector space and transform these subspaces with one automorphism of the vector space simultaneously, move them around. How can you classify them? So triples of subspaces U1, U2, U3 in a fixed vector space up to transforming them to GU1, GU2, GU3 via, again, some invertible operator. And how can we classify the relative positions of three subspaces? And again, well, this could be one of the harder exercises in a linear algebra course. It's a discrete classification problems, and it involves only discrete parameters. That was me, that was feedback from me, I think. Okay, so it only involves discrete parameters, namely, well, you can look at the dimension of these subspaces, the dimension of their intersections and sums of intersections, intersections of sums, and you write down all the discrete parameters which you can guess, and that does the trick. So this has a discrete classification. And now you can guess what happens. We increase the number of subspaces, and then the problem becomes more difficult. Let me just briefly indicate this. And then we have enough linear algebra problems at hand. So C2 is the analogous problem of quadruples of subspaces. This is a problem which is still solvable. And it already involves continuous classification parameters, which you can see from something very classical, namely from classical projective geometry. So it involves discrete and continuous parameters. And again, let me ignore the discrete ones and let me concentrate on the continuous parameters and just show you one example where you have continuous parameters. Namely, let's consider four one-dimensional subspaces in a two-dimensional vector space. So four lines, L1, L2, L3, L4, are four lines in a two-dimensional space. Well, the lines in a two-dimensional space are the points in the corresponding projective space. So these are 4 points in the projective line. And now very classical geometry tells you the relative position of 4 points in CP1 involves a continuous parameter, namely the cross ratio of these 4 points. So there's a continuous parameter. It's the cross ratio from classical projective geometry. Yeah, and there you see the continuous parameters entering. But again, if you look at the full classification, well, the discrete part becomes even more involved, but it's still discrete, and the continuous part is, well, not worse than that, except for looking at lots of different cross ratios. It's nothing else. So again, the number of continuous parameters grows linearly with the size of the problem. And finally, guess what? Quintuples of subspaces. That's an unsolved problem. Well, okay. So that was 9 problems of linear algebra. Now you might ask, maybe that was a bit too much. 3 or 4 problems would have sufficed. But I told you about these problems because in these quite unexpected applications of Quiver moduli spaces, precisely these classes of problems enter. So the class A of problems, simultaneous similarity of square matrices, will enter maybe even today when we talk about Euler product factorizations. The series B enters in writing down quantum dilogarithm identities, and the series C is responsible for computing Gromov-Witten invariants for us, quite surprisingly. So these are precisely the series which we will see in the applications in later talks. So let me just show you a little overview over these problems. A1, A2, A1, A2, A3, B1, B2, B3, C1, C2, C3. And for the first problem in all these classes, we had a discrete classification. In the second line, we have discrete plus continuous, but the continuous parameters grow linearly with the size of the problem. And in the third line, we have all the unsolved linear algebra problems, and the number of continuous parameters grows quadratically. So the number of continuous parameters is quadratically in the problem. Okay. So that was lots and lots of problems, and 3 of them largely unsolved. If you have any ideas for attacking this classification, that would be fantastic. And the next step would be to find a unified language for such problems. But maybe this is already the right point for, yes, this is already half of the talk. So maybe that's maybe the right point for questions.
Yes, so people who have questions can now unmute themselves. There is one question by Ian Lee, so feel free to ask the question yourself, or otherwise I will read it aloud.
I was just thinking, it seems natural to have problems B0 or C0 where you have 2 subspaces in a vector space, or B0, I guess, would be just 2 spaces without a map between them.
Yes. Consequently, yes, that would be a good idea. Yes, of course. Well, one should say C1 is something like 0, 1, 2, or 3 subspaces. They all have a discrete classification. And B0 would be just 2 vector spaces without a linear maps. And then the only invariants are, again, the dimension of the 2 vector spaces. And A0 would be just no information at all. We even forget the vector space, so then the classification is void. But yes, that makes sense. Well, right, yes. The surprising thing is that you have this well, you have this harmless region, which you can treat in linear algebra of problems with a discrete classification. Then there is this thin line where you can solve it by something more or less equivalent to the Jordan canonical form, and then you jump out into the wild, and nothing is solved. Yeah, and it's this trichotomy, which is also a technical term in the representation theory of quivers, which we will discuss. And this I wanted to somehow illustrate. But you're right, you could probably do problems 0.
Okay, thank you. I also have a question.
Yes, please.
Is question C3 solved for an arbitrary number of spaces in C2? Because that would be points on P1. So that would be M0.
If you would, well, even then there are many mysteries about these spaces. So what you can then say, well, there are moduli spaces parameterizing stable. Okay, I'm somehow talking about things I will discuss tomorrow or maybe next Monday. You can define moduli spaces of stable such configurations, and well, coordinates for these moduli spaces are known, quite efficient coordinates from a paper by Howard, Milson, Snowden, and Wackel. And well, but how much about a variety do you know when you know explicit coordinates and defining equations? That's the problem, right?
Mm-hmm.
You encounter, well, the first thing, well, here you encounter, when you have the cross ratio is an element of CP1 again. So in effect, the moduli space is CP1. The next one is the degree 5 del Pezzo, so quite prominent. With 6 of them, you get the Segre cubic, which is singular threefold, but with isolated singularities. And then maybe for 8 or 10 points, something appears in classifying hyperelliptic curves, I think. But I mean, otherwise you can write down these varieties, but there are no names for them in general. Yeah, they are always Fano. That's all I know at the moment. Yeah, so they are known in that you can write them down explicitly with coordinates, but quite a lot of their structure needs to be explored, and that's only for a 2-dimensional space.
Yeah, sure. Yeah. Thank you.
Can I just comment a little bit?
Yeah,
sure.
If you fix the dimension, then the problem is solved. You can just put in the computer all your problem, and in principle, it will give you equations, right? The point of this is that this problem is unsolved because it's unsolved for all dimensions. That's the difference, right?
Yes, you cannot solve it uniformly, but also, I mean, in any fixed dimension, yes, you can put it in a computer in the sense that you could find defining coordinates and defining equations for these moduli spaces, which I would like to introduce. But well, this is very quantitative, and you don't know anything about the quality of the resulting spaces. Yeah. So I mean, in principle, yes, you can do this, but I will tell you. Okay, let me give you one example. I want to do this later, but let me give it to you now. Look at triples of 3x3 matrices under simultaneous conjugation. That's maybe the most difficult case which can be solved. So triples of 3x3 matrices, you can embed the moduli space, whatever it is, into a 48-dimensional space and defined by 365 explicit equations. That's easy to memorize, yeah? 365 days per year and 48 hours per day. And so, I mean, it can be done, yeah? But this is let me check. This is a 19-dimensional affine variety given by 365 equation in 48-dimensional space. So you don't know anything about that. Yeah, I mean, you could do it in any dimension if your computer is powerful enough, but you don't understand the quality of the classification problem, and you don't have a uniform normal form for solving this. Yeah, that's true. I mean, there are yes. So the question is, what would you accept as a solution to the classification problem? That's indeed a very good question. There's also the point of view if this is classifiable in a somehow logical or model theoretic sense. So in the sense of, is it computable? Can you find a Turing machine which classifies these things for you? And in general, these are somehow unclassifiable in the sense that a Turing machine can't do. but we are mathematicians. We can do more than a Turing machine. We can do maybe something qualitative. So yes, it's very debatable what classifying actually means and what a normal form should be. But I would really call these problems unsolved in general. So next step is we will formulate a unified language for such linear algebra problems, or for the class of linear algebra problems which we will be interested in this lecture series, and that is the class of quiver representations. And we will look at these quiver representations from 2 points of view. One is purely algebraic or representation theoretic, and one is more geometric. And then I will comment on these two different approaches, and we will see what they are good for. Okay, let me check the time, 45. Okay, so that was the introduction, and now let's come to, introduction was maybe part 1, and now let me come to part 2, quiver representations. And 2.1 will be the more algebraic or representation theoretic approach, and the other part will be the more geometric approach. So the algebraic approach is the following. So what is a quiver? A quiver is nothing else than a colorful name for an oriented graph. Q is a quiver. It's an oriented graph. And what do you need to define an oriented graph? You need a set of vertices of the graph, which we'll call Q0, and you need a set of arrows. So for unoriented graph, you would call this an edge, and here it's an arrow because there's a direction, and I will write all the arrows like I write maps. So an arrow is called alpha, and it's an arrow from vertex I to vertex j, and the collection of all these we will always denote by Q1. So that's the data of an oriented graph, a set of vertices, a set of arrows, and for each arrows you need to know its source and its target vertex, which you can formalize in 2 maps from Q1 to Q0. So why do we call this a quiver and not an oriented graph? Well, this colorful terminology is due to Gabriel, who started this quiver representation theory, and a quiver is something containing arrows. That's why it's called a quiver. That's it. And we allow these quivers to be quite arbitrary. So there might be cycles, oriented cycles. There might be even loops at a vertex. There might be parallel arrows. It's all fine. The one thing I would like to assume for simplicity is that both sets are finite, which you would call then a finite quiver. Yeah, but I mean, that's just a technical assumption. Let's assume they are finite for a moment. Okay. Typical example would be something like this, or this, or this. This would be typical quivers. Or maybe let's do this one. Or maybe some more. All these are perfectly valid oriented graphs. And now we define what is a representation of this. And the idea is the following. You represent an oriented graph by representing the vertices in vector spaces and representing the arrows in linear maps. Finite dimensional, complex representation of Q is a tuple. We always call these representations V, and it's a tuple consisting of a tuple of complex vector spaces and linear maps. I will decorate this in a second. Is a tuple where each VI for each vertex is a finite dimensional C vector space. finite dimensional C vector space. And this is a C linear map. That's a representation of a quiver. You represent the vertices in vector spaces and the arrows in linear maps. And now you could already talk about a classification problem if we have a notion of equivalence for such configurations of vector spaces and linear maps. We will do this bit better. We will just talk about a notion of a morphism or map of quiver representations. And if we have such a map and it behaves nicely, then we already know what an isomorphism or an equivalence is. A morphism phi from a quiver representation V to a quiver representation W is a tuple of linear maps again, linear maps phi I from the vector spaces Vi to the vector spaces Wi, I indexed by the vertices, such that all diagrams commute. That's the easiest way to formulate, such that all diagrams commute. That's the only thing you have to memorize, and then in any situation you can work out what are these diagrams which are assumed to commute. I will show you. That is, for any arrow alpha from I to j in our quiver, we now have a diagram, namely part of the datum of a quiver of the quiver representation V is the map, the linear map F alpha from Vi to Vj. Part of the datum of the quiver representation W is a map, say G alpha from Wi to Wj. Part of our datum for a morphism are maps phi I and phi j. So here's the diagram you can ask to commute. Okay, so that's the notion of a morphism of quiver representations. And now you can, well, easily check, if you are into categories, that all this forms a very nice category. The objects are the representations, the morphisms are these morphisms, and now you just have to invent the composition of morphisms, while in lack of any more, of any better idea, just compose morphisms component-wise. And that does the trick, yeah? So this defines a very nice category structure. Or a more fancy way of saying this is the following. What I'm writing down here is just a category of functors. Yeah? Out of this oriented graph, you can build a small category. The vertices are the objects, the arrows are the morphisms. And then the datum of a quiver representation is nothing else than a functor from the small category to vector space, finite dimensional vector spaces. And the notion of a morphism is precisely the notion of a natural transformation of functors. So we have a functor category and we have all the good properties of functor categories, if you are into categories. Okay, so, but in particular, what we have now is a notion of equivalence or isomorphisms. What are isomorphisms of quiver representations or equivalences? Well, these are morphisms which are invertible, which in our case just means all these phi I should be invertible maps. Yeah, but let me summarize all this in one big fact, which was somehow how Gabriel started the representation theory of quivers. Quiver representations form a category. Let me call it rep CQ. Capital rep would be for arbitrary, maybe infinite dimensional representations, and lowercase r would be for finite dimensional representations. That's the base field, that's the quiver. This category, which is, well, it's C linear, so we have a linear structure, a vector space structure on morphism spaces. It's a abelian, very nice, it's an abelian category. It's also a finite length category, and maybe other good properties, which we'll come to later. So that means it behaves like a category of modules over some ring. And in fact, it is a category of modules over some ring, which we just don't need at the moment. We'll come to this later, maybe. But at the moment, it's just, well, we can define a notion of isomorphism. We can talk about sub-objects, and they behave like sub-objects and isomorphisms and quotient objects usually do, because we have a nice abelian category. We even have analogs of the classical theorems of module theory. We have finite length categories, so we can form composition series. We have the Jordan-Hölder theorem, and so on and so on. So many things which you know for module theory hold for quiver representations. That's great. Okay, now finally let's go back to, okay, I need one definition, one technical notation, which we'll use all the time. Notation, the notion of a dimension vector. The dimension vector. A quiver representation not only has a dimension, it has several dimensions, namely the dimensions of the vector spaces which are involved. And this we call the dimension vectors, boldface dim, of V. This is just defined as a tuples of the complex dimensions of all the vector spaces Vi constituting the representation, and this is viewed as an element n to the Q0. That's a dimension vector. This is a notation which we'll need all the time. Now let's identify the problems in the introduction. All classification problems, that's important to note, all classification problems in part 1 are classification problems for isomorphism classes of quiver representations. So that's the first exercise, which you can easily solve at home if you just look again at these classification problems which I posed. So so we had the problems A, B, and C, and 1, 2, 3. A1 is just the quiver which consists of a vertex and no arrows. A2 is the problem of a single vertex and a loop. And problem 3 was pair of loops. B1 was a single arrow. B2 is parallel arrows. And B3 is triples of parallel arrows. I will just complete this diagram and then explain one of the entries. And C is essentially the series of 3 vertices pointing to 1, 4 vertices pointing to 1, and finally, quintuples, 5 vertices pointing to 1. So let's pick one of these problems. Please recall A2 and B1. Let's recall, let's start with B1. The classification problem for B1 was a single matrix up to row and column operations. Or in more invariant terms, a single linear map, and we are allowed to perform base change in both source and target space. That's precisely what a representation of this quiver is. It consists of 2 vector spaces and a single linear map. And in the notion of morphism, you have one phi I, which for an isomorphism, sorry, I think for you to see this, I have to move the blackboards. In the notion of morphism, you have one phi I, one base change operator in a sense for each vertex. So that means in formulating isomorphism classes for this quiver, you have the freedom of performing a base change here in the source and in the target. That was precisely our classification problem. And as a second example, let's do A2. What is a representation of A2? You have a single vector space and a map from that vector space to itself, so an endomorphism. And what are you allowed to do with this endomorphism under the notion of isomorphism? You are allowed to just perform one base change in the vector space. You just have one of these maps phi. And that precisely translates into the linear algebra problem of conjugacy of square matrices. Yeah? So these are the series of curves we deal with. All right. So now we have set up this this categorical language, or algebraic language for curve representation. And let me now state one of the main theorems, which is in fact a combination of theorems from many different people. And I will also state it a bit informally, which has the advantage of hopefully giving you a feeling for that and somehow connecting it to the problems in part 1. And this theorem is the trichotomy for quiver representations. So this is the theorem which I should attribute, well, first part to Gabriel, then Nazarova-Reuter, and also Donovan-Freislich, Victor Katz, and I think many other people. Well, maybe I forget a few names. You can't sue me for that because the theorem will be formulated in an informal way. When you try to classify the representations of a quiver, when you try to solve this corresponding linear algebra problem, there will be 3 cases. Either you only have discrete parameters appearing in the classification problem, or you have discrete and continuous parameters, but the continuous parameters are as harmless or not as the Jordan canonical form, or you are out into the wild and everything can happen. So this is the so-called trichotomy. So part 1, this is essentially Gabriel's theorem. The classification of objects in the category rep CQ, and the classification of objects, here again I mean for all possible dimensions at the same time, involves only discrete parameters. And more precisely, this means, what does it mean to have this discrete classification? That means for any fixed dimension, you only have finitely many types, isomorphism classes. So equivalently, for fixed dimension vector D, there are only finitely many isomorphism classes of representations. So this is equivalent to a theorem, to a fact which you can just see directly from the graph itself. Namely, you take the underlying unoriented graph, which just means forget about all the direction of arrows. So this is the unoriented graph. And this is a disjoint union of ADE Dinkin diagrams. It's a disjoint union of AN, DN, E6, 7, 8. Dinkin diagrams. So the famous Dinkin diagrams appearing in, well, almost everywhere in mathematics, in the classification of complex semi-simple Lie algebras and, well, wherever you have seen them. Okay, so this is a precise criterion for the classification problem only involving discrete parameters in all possible dimensions. That's nice. Okay, so second step is discrete and continuous parameters. And The second part is there are, in the classification problem, continuous parameters but their number are only growing linearly with the dimension. Their number growing linearly with the dimension vector. This is equivalent to the unoriented graph being an extended Dinkin diagram. This is a disjoint union of AN tilde, DN tilde, E6, 7, 8 tilde, extended or affine or Euclidean Dinkin diagram. And actually this property of linear growth of the number of continuous parameters is also equivalent of the problem being as difficult, of the continuous part being as difficult as the Jordan canonical form for one matrix. To formulate this precisely requires lots of notation. That's the notion of tameness of a module category. So I will omit that. And the important thing is that's just this linear growth of the number of continuous parameters. And okay. So that's this fine border of the problems A2, B2, C2. And in fact, if you look at these problems, A2, that's an A0 tilde extended Dinkin diagram. B2, that's a A1 tilde extended Dinkin diagram. And C2, that's precisely a D4 tilde extended Dinkin diagram. Okay. And third part of the theorem is everything else is totally wild. So third part is otherwise. So if you don't have Dinkin or extended Dinkin type for your graph, otherwise the number of continuous parameters usually grows quadratically. Number of continuous parameters grows quadratically in the dimension vector. Okay. So that's something we have observed, or I have told you about in these classification problems in the first part. And now it's manifest in this theorem. This is really the general behavior. Yeah, and there's nothing in between. All right. So we are interested in moduli spaces, or I am interested in moduli spaces, and this is what this series is about. These moduli spaces encode all these continuous parameters. In the first case, there are no continuous parameters at all. And we will see formally, this means all these moduli spaces are just empty or single points. There is no geometry behind them. In the second case of linear growth of the number of parameters, these extended Dinkin diagrams, you can look at these moduli spaces, but they are harmless, yeah, because of this linear growth. The moduli spaces you get are a series of affine spaces or of complex projective spaces, really well understood spaces. And so the only case where these Quiver moduli spaces are really interesting is otherwise, yeah. If your continuous parameters really explode in number, and then the moduli space are interesting. Let me make this clear. So that's the only thing, that's the only situation where moduli spaces are interesting. Here, moduli spaces are interesting. And only here. And almost all the notions which I will define in the next talks to deal with these moduli spaces, almost all of these notions might make sense in these two cases above, but they're not terribly interesting there. So that's this otherwise, this out in the wild, that's precisely where we're aiming at. Okay, I have some more minutes left, I think, like 6 minutes or so. And let me tell you this other approach, and then I will stop. Let me tell you the geometric approach to quiver representations. And this geometric approach, in fact, will be the approach which we take to define these moduli spaces. Well, after all, these moduli spaces are objects of geometry, and we should have some geometric approach. This geometric approach is just one key observation, just a tautological reformulation, but this is important to understand this point, so I really want to make it clear. So for this geometric approach, let us fix a dimension vector, D. So this is a whole tuple of dimensions encoding these vector spaces. And we fix this dimension vector, and for each of these, we fix the vector space. Well, fixing the vector space, if we have fixed the dimension, is completely harmless, because we know that up to isomorphism, the vector spaces involved in the quiver representations only depend on the dimension anyway. Yeah? So if we have fixed the dimension, we could also say, let's just fix the vector spaces. Fix the vector space Vi of dimension Di. These are the entries in the dimension vectors. And let's do this for all the vertices of the quiver. Okay. So now we have fixed the first part of a quiver representation, this tuple of vector spaces. What about this other datum, the tuple of linear maps? All the possibilities for the linear maps we will now encode in a big space, actually an affine space. Let me call this just representation space. And I will denote it by Rd of Q. This is just the direct sum for all arrows of the quiver of the C linear homomorphisms from the vector space Vi to Vj. So this is a universal space encoding quiver representations, because a quiver representation consists of the vector spaces, which we have already fixed when we fixed the dimension, and of the linear maps. And well, a point in here is just a tuple of linear maps, a configuration of linear maps. So the points in Rd of Q correspond precisely to the tuples F alpha from Vi to Vj along all the arrows, which constitute a quiver representation. Fine. What is this? Well, Vi and Vj are vector spaces, so the linear maps form a vector space, and we take a finite direct sum. So it's all a big vector space. We can just treat it as an affine space, but it's just a complex vector space again. On this complex vector space, I will now define a group action. By a group GD, which is the product over all vertices of the general linear group Vi. So this group encodes all the base changes. There's one automorphism in this copy GLVI for each of the vertices. Yeah? So an element in here is a whole tuple of elements which are automorphisms of the individual vector spaces, so we can perform base change along these automorphisms. And now we have an action, and the formula for this action is really a formula resembling this notion of equivalence which we have seen in the first part. So let's recall, how was this notion of equivalence formulated? For example, in the problem A2, the problem of conjugacy of matrices, we had this formula S times A times S inverse. In problem B1, we had this formulation for equivalence of rectangular matrices. This was something like S times A times T inverse. So it always looks like a kind of conjugation or adjoint action if you want. And having this in mind, that this should be something like conjugation, you can already guess the formula. Yeah? So just remember that this is some kind of conjugation, and then you guess the formula. A tuple of group elements, GII, acts on a tuple of linear maps, alpha, by GJ F alpha GI inverse if alpha is an arrow from I to J. That's the only way to write down a conjugation which makes sense. Yeah? GI is the base change in the source. Then you map with F alpha to the target space Vj, and then you perform base change there. So this is an action. This is actually a linear action. Linear action because it is linear in F, which you can see manifestly from the formula. There's a linear action of the algebraic group GD, or if you don't want to call it an algebraic group, call it a complex Lie group. The algebraic group GD on the complex vector space RD of Q. And now comes the key observation. Which is really tautological. It really follows from the definition, but it's the key observation to do geometry of quiver representations. The key observation is that the orbits for this group action are precisely the isomorphism classes of quiver representations. So the orbits of this group in this space correspond bijectively and canonically to the set of isomorphism classes of representations of the chosen quiver Q of this fixed dimension vector D. Why? Well, just look at this formula and assume that you have another representation given by F alpha prime. Let me just do this key calculation. If F alpha prime equals GJ F alpha GI inverse, you can reformulate this as saying F alpha prime composed with GI equals GJ composed with F alpha. That means a certain diagram commutes. This diagram commutes. And this diagram we have seen when we defined the notion of a morphism of quiver representations. Now, these GI, GJ are precisely elements in this group of automorphisms, so they are isomorphisms. So that means precisely the representations defined by Vi and F alpha, and the representation on these vector spaces defined by the F alpha prime are isomorphic in this category of quiver representations. Yeah? So this is this key observation. So we have seen that we can reformulate the problem of classifying linear algebra objects, configurations of matrices. We can first reformulate it in the language of quiver representations, and from there we can translate it into a problem of classifying orbits for a group action. And this now opens a perspective to defining moduli spaces. So what is the object classifying orbits in a group action? Well, it's the orbit space, right? So our naive idea would be to say moduli spaces, so geometric object encoding this problem or this classification of linear algebra should be something like taking the quotient, taking the orbit space for a group action. Well, the problem is that you can do this set theoretically or point set topologically, but you get something very, very bad. And so we have to be extremely careful about forming this quotient. But that's the idea which we have distilled out of this key observation. If we want to have spaces, geometric objects encoding the classification, we should do something like forming orbit spaces. And this we will do tomorrow. But just one final remark. We now have two approaches to our linear algebra problems, one in a categorical language and one in a geometric language. And the great thing is that you can play these two approaches against each other. Or you could say, for doing algebraic geometry of moduli spaces, it is not only important to have this geometric approach here, but having this category of representations as a backbone for the whole thing, connecting all these individual orbit space problems. And this will play a major role in studying these moduli spaces, which we'll define tomorrow. That's it for today. Thank you very much for your attention.
Thank you very much, Markus. If there are any questions that you want to be recorded or you don't mind that they are recorded, you can ask them now.
So in hey, hello. In the classifications, well, kind of in this 3 cases that you wrote down, 1, 2, 3.
Yes.
Can you give a general idea how you can prove it for 2 and 3? So in the first one, you do it by classifying all indecomposables that you can reduce.
Right. Gabriel's theorem works by classifying. I mean, you have, because this is a finite length category, you have the theorem of Kroll-Remarque-Schmidt. You can decompose everything into finite direct sum of indecomposables. So you only have to classify the indecomposables. And this you can do systematically. Well, usually by looking at, say, reflection functors, and reflection functors produce all the indecomposables in a certain pattern out of the simple representations. So you can really classify the indecomposables and you are done. For the second case, you do the same. You basically classify all the indecomposables. You have a discrete part of the classification. And for those who know about the representation theory of Quivers, these are the pre-projective and pre-injective representations. And then you have a regular part for the classification. That's where the continuous parameter comes in, the regular, homogeneous and non-homogeneous tubes. So it's basically also by classifying the indecomposables. To have this third thing, well, for all other quivers, you cannot classify the indecomposables, but then you take this geometric approach of looking at orbits, and you realize that you have infinitely many dimension vectors where you have indecomposables, and then in almost all of these infinitely many dimension vectors, you have whole family of indecomposables, and you do a clever estimate of on how many continuous parameters it depends, and it turns out to grow quadratically in the dimension vector. Yeah? So that's the approach of cuts. You look at the indecomposables again. It's much more involved and completely geometric, this approach, but you basically write down the dimension vectors, the possible dimension vectors of the indecomposables. They're infinitely many, and you realize that the number of parameters on which they depend is large.
Thank you.
There's also one question from the physical audience, I think, I've been told. So, Markus, I think you have to repeat the question because otherwise people won't hear.
Oh, sorry, yes, I forgot this. Thanks. Thanks for the reminder, yes.
Yeah, I think there's one question.
Yes. Yeah.
Please repeat the question, though.
Okay, I will repeat the question. So if you know about the representation theory of finite dimensional algebras, when you have the notion of tameness, so tame, that's this small, thin line between discrete classification and completely absurdly wild classification. On this thin line, you might have different, even different growth behaviors, but that's this growth behavior, exponential, super exponential, domestic, whatever, that does not concern the dimension of the, so the number of independent continuous parameters, but it concerns somehow a discrete part in the continuous part. That means the following. So this thin line of tame situations is characterized by the fact that the continuous part is as difficult as the Jordan canonical form. But the question is, how many of these Jordan canonical forms discretely do you need to somehow cover all the indecomposer representations? Yeah, and even this number for quivers with relations, for other tame algebras, might grow exponentially. Yeah, but I'm considering here just as a very rough measure, just the number of independent continuous parameters, aka dimensions of moduli spaces, and that just grows linearly. Yeah.
Okay, thank you very much. I will now stop the recording, and
Okay.
then we can have some further informal discussion.